In this session, I would be talking about working with different kinds of functions of random variable, wherein I would be interested in creating the probability distributions or probability densities functions for functions of one or more random variables. So taking one or more random variables together, right? So x1 and x2. So if x1 is one random variable having one kind of a distribution, x2 is another random variable with another form of a distribution, then how do I combine these two things to really form another particular variable which is some kind of a function of x1 and x2. So initially we will look at functions of one variable, and then we will also look at how do I combine these variables to find their probability distribution or the density functions. So we will talk about primarily three major techniques. One being the distribution function technique to really execute the density function associated with a function of a random variable. Then we will do a transformation technique wherein we will look at example of one variable as well as several variables, and we would also use a moment generating function technique. So these are the three major techniques that we can use to work with functions of random variables. So we will get started here. So the intention of this session is look at the first bullet point. We are talking about a set of random variables x1, x2, xn, and I am interested in finding out their joint probability density function or the distribution function. It's also given, right? Individually the random variables are given, their joint probability density functions are given. Now I am more interested in finding out the probability density function or the distribution function of another function of these random variables. So x's are given. I'm interested in finding out y, which is some function of x1, x2, x3, so on. So the values of y are typically related to the values of x by this kind of an equation. So it could be a very simple equation involving only one variable, or it could be a very complex equation involving multiple variables as well. But wherever we have to solve these kind of functions, we generally talk about three major kinds of techniques, especially if I am interested in finding out their densities or distribution functions. I can use either a distribution function technique or a transformation technique with one variable or several variables, or I can very well use a moment generating function technique. So we'll go with one by one. In a distribution function technique, what is that we typically do is, whatever is the density function that you are given, you find the distribution function for it. And once you find the distribution function, then again compute back the density by doing the differentiation. This is for y. So if we are talking about finding the density function for y, first find the distribution of y. The distribution function is capital F of y, which is probability of y less than or equal to y, which is nothing but the probability of this function of x less than or equal to y. So you will, whatever is this function that is getting, you find the derivative of it to get f of y, which is the density function of y. So you always start with the distribution function of y and then move towards arriving the density function by doing a derivative of the density function. Probably one example would be very clear. If the probability density of x is given by f of x equal to 6x into 1 minus x, we are talking of x is only between 0 and 1, and this function is 0 elsewhere. I want to find out what is the probability of y equal to x cube. So if we follow the distribution function technique, right? So I want to find g of y, which is nothing but the probability of y less than or equal to y. Now we have, so we are saying y equal to x cube, right? So we have initially said the probability of y less than or equal to y is nothing but probability of x cube less than or equal to y, which also means probability of x less than or equal to y to the power of 1 by 3. So this is what I can very well find out. 0 to y to the power of 1 by 3, right? 6x into 1 minus x dx. So 6x, the integration is 6 into x squared by 2, which is 3x squared. 3x squared is, so y to the power of 1 by 3. So y to the power of 2 by 3. So this becomes 3 into y to the power of 2 by 3 minus 6x squared. 6 into x cube by 3, which is 2x cube. 2 into y. Y to the power of 1 by 3 to the power cube, which is y. So this is what is becoming g of y, capital G of y, which is the distribution function of y, is 3y to the power 2 by 3 minus 2y. So from here I can find out the density function of y, which is g of y. I will very well differentiate it 3 into 2 by 3 into y to the power of minus 1 by 3 minus 2, which is nothing but 2y to the power minus 1 by 3 minus 2. So this is what will become the density function, where y is lying between 0 and 1 and it is 0 elsewhere. So that's a simple way. First you find the distribution function, and based on that distribution function you take the derivative to get the density function. We'll take one more example. Y equal to mod x. Find g of y, where f of x is the probability density of x at x and g of y is the probability density of. So we know that g of y, when you are talking of y equal to mod x, g of y is nothing but is equal to, so first let's start with g of y. If we have to find this g of y, I require capital G of y, distribution first, probability of y less than or equal to y, which is nothing but probability of mod x less than or equal to y. So when mod x has to be less than or equal to y, it means that x has to lie between minus y to plus y. So minus y, so because when we are saying mod 3 less than or equal to, right, or mod x less than or equal to 3, it means x has to be lying between minus 3 and 3. So this is the same thing we are giving. Mod x less than or equal to y is nothing but y, x should be lying between plus or minus y. So which is as good as saying f of capital Y, sorry, this is minus f of capital Y minus f of minus capital Y. So because we are talking of probability lying between minus y to plus y, so I am finding the distribution function with respect to y, which is saying less than or equal to capital Y, minus distribution function of minus y saying value less than or equal to minus y. So I can very well find f of y minus f of minus y. So this is what is the function that is coming. So I'll take the derivative of this, right? This is what will become my distribution function. So I'm taking the derivative of it, which will give me f of y plus f of minus y. So the density function is going to come out as f of y minus plus f of minus y for y is greater than 0 and it is 0 elsewhere. So that's how we can very well solve the functions of random variables if we are going with a distribution function technique. In case of two variables, let's look at this example. Joint density of x1 and x2 is given by 6 e to the power of minus 3x1 minus 2x2, where x1 and x2 are greater than 0. Now I am more interested in finding the probability of x1 plus x2. So first let me find f of y. Probability of x less than or equal to y. Right? And we know f of y is x1 plus x2. Right? We are probability of y less than or equal to y, which is nothing but probability of x1 plus x2 less than or equal to y. So I can very well set, so the first one I can set it to 0 to y, right? Because if I want x1 plus x2 less than y, x1 I can integrate between 0 to y, but x2 I should integrate only between 0 to y minus x1. 0 to y minus x1, 6 e power minus 3x1 minus 2x2 dx1 dx2. So first I can integrate with respect to x2. So it becomes 0 to y 6 e to the power of minus 3x1 and e to the power of minus 2x2 will become e to the power of minus 2x2 by minus 2. This is getting integrated between y minus x1 to 0. So this I can simplify it, minus 3, 0 to y minus 3 I am taking out, e to the power of minus 3x1, e to the power of minus 2y plus 2x1, right, and minus 1. This is what is the integration value that is coming out, because minus 2 into y minus x1. So this is what is coming out, which again is working out as, if I take this internally, minus 3 into e to the power of y, 0 to y, e to the power of, if I take it internally, it is nothing but minus x1 minus 2y minus e to the power of minus 3x1 dx1. Now I'll integrate this with respect to x1. So the first one will become minus 3 e to the power of minus 2y into e to the power of minus x1 by minus 1. So the first one, this will become plus, and this is integrated between y and 0. Then minus 3 into plus minus e to the power, so it becomes 3 e to the power of minus 3x1, sorry, not minus 3x1, yeah, minus 3x1 by minus 3. This again is integrated between y and 0. So overall it is coming out as 3 e power minus 2y. This is integrated, this multiplied by e to the power of minus y minus 1 minus e to the power of minus, so this is minus of 1, right? So minus of e to the power of minus 3y minus 1. So overall is becoming like this, right? If you simplify it, it is nothing but 3 e power minus 3y minus 3e power minus 2y minus e power minus 3y plus 1. So it is becoming 1 plus 2e power minus 3y minus 3e power minus 2y. So this is what is becoming the capital F of y, which is the distribution function associated with y, is coming out as 1 plus 2e power minus 3y minus 3e power minus 2y. Now I can very well find out the f of y by doing the derivative of this with respect to y. So this is 0, 2 into minus 3 e power minus 3y minus 3 into minus 2 e to the power of minus 2y, making it minus 6 e to the power of minus 3y plus 6 e to the power of minus 2y. I can very well write it as 6 e to the power of minus 2y minus e to the power of minus 3y. So this is the density function that is coming out for this joint, based on the joint density function coming out for x1 and x2. I have transformed it to find the joint density function associated with x1 plus x2. So especially if we want to find the function of another variable based on the existing random variables, we can use the distribution function technique, where we are first finding out the probability of capital F of y, which is probability of y less than or equal to y, and then we are going ahead in terms of differentiating it to get the density function. Alright, now we'll move on to the next technique, which is the transformation technique. Initially we'll go with one variable transformation, then we will also look at examples of multivariable transformations as well. Now in this, when I look at a discrete distribution, it's not a big problem. As long as the relationship between the values of x and y is 1 to 1, for each value of x, there is a different value of y. So as long as you are having that kind of a 1 to 1 relationship between the values of x and values of y, it's a simple substitution, and which is what is giving us the function of a random variable. If I want the probability distribution, let's say I have a probability distribution function of x, and I want to find out a probability distribution function of 1 by x. As long as these two have 1 to 1 kind of a relationship, there is nothing that is stopping me from a simple substitution. The probabilities will not change, but they would be associated with the newer values of y. That's the only thing. Probabilities will not change at all. If you are saying what I am trying to refer to, x is the number of heads obtained in 4 tosses of a balanced coin. Find the probability distribution of y equal to 1 by 1 plus x. So we know that in case of x, it can get 0 heads, 1 head, 2 heads, 3 heads, 4 heads. And the probability associated with it, getting 1 head, 1 by 16 chance, 0 head, 1 by 16, 1 head, 4 by 16. This is a binomial distribution. 2 head, 6 by 16, 3 heads, 4 by 16, and 4 heads is 1 by 16. Now someone has asked me to find out what is the probability distribution of y, which is 1 by 1 plus x. In this case, only the x will change. When x is 0, 1 by 1 plus 0, which is 1. X is 1, 1 by 1 plus 1, which is half or 0.5. And this is becoming 1 by 3. This will become 1 by 4. This will become 1 by 5. But the probabilities will still remain the same. So in case of discrete, what we generally find is it's just a simple substitution. right? I am getting the distribution function associated with y straightforward, wherein I am substituting the values of x in the y to get the various other values of y. But on the other side, if we see the probability distribution, if I want z x minus 2 whole square, right, with respect to the same example, if it is y equal to 1 by 1 plus x, we are able to do it quite comfortably. But if you see the same x equal to 0, 1, 2, 3, 4, f of x we have got it as 1 by 16, 4 by 16, 6 by 16, 4 by 16 and 1 by 16. Now if you look at z, which is x minus 2 whole square, 0 minus 2 whole squared is 4, 1 minus 2 whole squared is 1, 2 minus 2 whole squared is 0, 3 minus 2 whole squared is 1, 4 minus 2 whole squared is 4. So now you see there are two different values here. Here also it is corresponding to two different values. So my density function will change altogether. It can come only three possible values, 0, 1, 4. And now the f of x is 1 by 16 plus 1 by 16, which is 2 by 16 is the probability here. 4 by 16, 4 by 16, which will translate to 8 by 16 for 1. For 0 it is 6 by 16. For 1 it is 8 by 16 and for 4 it is 2 by 16. So this is how my distribution function will slightly change if there is no one-to-one correspondence between the variables. But if each value of x is going to result in a completely different value of y, then it's a straightforward substitution. There is no other additional piece of work to do in that case. But if in such kind of an example where there are one value of x or two different values of x are leading to one single value of y, then we have to be slightly careful in terms of executing this particular function, right? We have to be slightly integrating all that stuff to work out with the variables. Whereas when you come to the continuous case, it assumes that the function y equal to u of x, whatever is the function of the random variable that we are taking, it assumes, the transformation technique simply assumes that it is differentiable, and at the same time it is either a continuously increasing function or a decreasing function. It should be either an increasing function or a decreasing function for all the values within the range. And it also assumes that the inverse function, which is x equal to w of y, will exist for all the corresponding values of y, and it is differentiable. So these are some of the important aspects if you have to use the transformation technique for finding the probability distribution function associated with a continuous variable. Let's take an example which will give us the confidence. If x has an exponential distribution given by, so we are having f of x equal to e to the power of minus x. I want to find the probability density of the random variable y equal to square root of x. Alright. So I am saying y equal to square root of x. So I have to really see whether this is differentiable. Right? Because we are finding this is a value between x and y. And if you look at the inverse function, x is nothing but y squared. So there is an inverse function, and this inverse function needs to be a differentiable as well. So if I am taking a differentiation of this, it is nothing but 2y. So all these are very much met. So first thing, when you are talking of y equal to something, couple of things that I want to check before I go ahead with the distribution, before I go ahead with this transformation technique is, I have to relate the values of x and y. So we are talking of x is nothing but y squared, which is the inverse I am able to express x in terms of y, and this is a unique inverse. And at this, because we are talking of x is greater than 0. For x is greater than 0, it's a unique value for every value of y. And we are also saying 2y, which is the derivative of x with respect to y, it is differentiable. So I can very well write g of y as, the way we can write it here is f of w of y multiplied by w dash of y. So I can very well write now f of w of y. So the w of y here for me is x equal to y squared, and f of that e to the power of minus y squared. Right? In this case, if I want to find the density function of y, we will write it as, first we'll get the inverse function of x. So the inverse function of x is y squared. That inverse function of x we will establish as the density function of x e to the power of minus y squared, and we will also take the derivative of y, derivative of x with respect to y, which is nothing but 2y. So this becomes 2y e to the power of minus y squared. This would be the function with respect to this would be the density function of y equal to square root of x. Right, so this is one more way of finding the density function of y. So if you look at the process once again, so I was asked to find the function of y equal to square root of x. So I am trying to first find x in terms of y, which is nothing but the inverse function. I have to see whether this inverse function that I have got is differentiable, because these two inputs I am going to use. Now I will take directly, if I have to find my g of y, it is nothing but I'll take the f of whatever is the inverse, right, f of y squared plus multiplied by the derivative, which is 2y. F of y squared is nothing but e to the power of minus y squared multiplied by 2. This would form my density function. A simple straightforward example. If x has the standard normal distribution, right, x is having a standard normal distribution, I want to find the probability density of z equal to x squared, and z is decreasing for negative values of x, right? So we could see for negative values of x, z equal to x squared, when I am taking for negative values of x, it's a decreasing kind of a function, and for positive values of x, it's an increasing function. But we have said that it has to be either increasing or decreasing altogether. So this is where we have to slightly change our approach. So we can, if at all, also these kind of functions straightforwardly, they cannot be taken up, because it's not a continuously increasing function or decreasing function. But I can think of transforming x to z, wherein first I can find out an intermediate variable, which is y equal to mod x, right, and use that. So when I want to try to find out the y equal to mod x, earlier we have already done, I can get my g of y as 2 by square root of 2 pi e to the power of minus half y squared. This is what we have got as the density function associated earlier. So then I can take z equal to y squared. And if I am taking z equal to y squared here, I can very well find the inverse of it. y is nothing but z to the power of half, and I can also see that there is a derivative of z also that could be created, half z to the power of minus half. So I can very well find out the density function of z by taking 2 by square root of 2 pi e to the power of, I have to establish as f of g of y. I mean f of the function. So e to the power of minus half z and the derivative of it, half z to the power of minus half. So this is what typically can become the inverse function. So in some cases, when we can't directly find out the inverse function because it's either an increasing or a decreasing function, I can take the help of an intermediate function, right? Because if we know that if x is having a standard normal distribution, then y equal to mod x will have a probability density. Earlier we have already proved the y equal to mod x is having a probability density of 2 by square root of 2 pi e to the power of minus half y squared. So I'll use that relation that we have derived earlier. Now if you see, if this I am taking as f of x, then the question that I am asked to find out is z equal to y squared. Now I will take the inverse. So if I have to use the transformation technique, I'll say y equal to z to the power of half, and even z to the power of half is differentiable also, half z to the power of minus half. So I can directly take, so if this is g of y, my h of z is nothing but g of the inverse of y. The inverse of y is nothing but z to the power of half multiplied by the derivative of y, which is nothing but half z to the power of minus half. So g of z to the power of half is nothing but 2 by root 2 pi e to the power of minus half y squared. So we already have got e to the power of minus half y squared. So I can very well take it as z, instead of y squared I could take z to the power of half. So z to the power of half squared is becoming z. So this will become 2 by root 2 pi e to the power of minus half z into half z to the power of minus half. So this would become the probability density function of z to x squared. So we could very well see that this transformation technique can help me, especially if there is an inverse function existing, and if this inverse function is differentiable, I can very well find out the probability density function associated with any other function of the random variable as well. The same logic I can extend it to multiple variables also, right? We have just looked at z equal to x cube kind of stuff where only one variable has been involved. But even if I have a joint distribution of two random variables x1 and x2 given, and I want to determine the probability distribution or the density function of a function of the random variables u of x1 and x2, still we can employ the same kind of a technique. Let's look at an example, one in a discrete case, one could be in a continuous case. If x1 and x2 are independent random variables having Poisson distributions with parameters lambda 1 and lambda 2. So obviously we get f of x1 is nothing but e to the power of minus lambda 1 to the power x1 by x1 factorial. F of x2 is nothing but e to the power of minus lambda 2 to the power x2 by x2 factorial. Now because they are independent, okay, I am asked to find the probability distribution of the random variable y1 y equal to x1 plus x2. First let me find their joint distribution. The joint distribution, because they are independent, I can very well take the product of their individual distribution, which is what is coming out to e to the power of minus lambda 1 plus or minus lambda 2, right? So it is coming out as lambda 1 to the power x1, lambda 2 to the power x2 divided by x1 factorial x2 factorial. This is what is given the joint probability distribution of f of x1 x2 for different values of x and values of y. Now I want to find out between y for y equal to x1 plus x2, right? So which means x1 is nothing but y minus x2. So wherever I am getting x1, I will substitute y minus x2. So let me find g of y comma x2. So x1 I am removing from the plane, wherein I am taking e to the power of minus of lambda 1 plus lambda 2, lambda 1 to the power y minus x2 into lambda 2 to the power x2 divided by x2 factorial into y minus x2 factorial. So now we got the joint density or joint distribution function existing between y and x2. Now I can do the summation. Now I can do the summation, especially with respect to x2. x2 can be from 0 to y, and x1 will be y minus of x2. So x2 I can do the summation from 0 to y. So I'll do a summation 0 to y with respect to x2. So which will come out as, if I'm taking out e to the power of minus lambda 1 plus lambda 2, which is a constant out. So because x2 is from 0 to y, this is constant. This becomes lambda 1 to the power y minus 0, which is y, and lambda 2 to the power 0 plus lambda 1 to the and this is becoming lambda 1 y divided by x2 factorial, which is 0 factorial, y minus x2 factorial, which is y factorial. Similarly, if you see for all, even if you take x2 equal to 1, it becomes lambda 1 to the power y minus 1, lambda 2 to the power 1 divided by x2 factorial is 1 factorial into y minus 1 factorial. Right, so I can very well, so I'll get it as 1 factorial by y minus 1 factorial. So what I will try to do is, I'll take out the y factorial out, and now I'll try to do the summation of x2 from 0 to y. Because I have divided by y factorial, I'll also multiply by y factorial. Now this comes as x2 factorial into y minus x2 factorial. Looks like a binomial distribution here. NCX y factorial divided by x2 factorial y minus x2 factorial. And this is becoming lambda 2 to the power x2, lambda 1 to the power y minus x2. So now you could see this is nothing but this entire thing is 1 because it's a binomial distribution. Right, when I am taking that out, it is coming out to be a binomial distribution itself. E to the power of minus lambda 1 plus lambda 2 by y factorial. And if you see this whole thing, it is getting expanded to lambda 1 plus lambda 2 to the power y. Right, because this is nothing but it's a binomial expansion. So the whole thing is working out to e to the power of minus lambda 1 minus of lambda 1 plus lambda 2 divided by y factorial, and this is coming out as lambda 1 plus lambda 2 to the power y. So the things are getting simplified like this, and this is what the sum of two independent random variables having Poisson distributions with parameters lambda 1 and lambda 2 are also having a Poisson distribution with parameters lambda 1 plus lambda 2. We are able to find that out, right? So I can very well use this result for any other mechanism as well. So we are able to use the transformation technique wherein we substituted y equal to x1 equal to y minus x2. So wherever x1 came, we have substituted it with y minus x2, summed it over all values of x2 to establish everything in terms of y. The same logic in case of continuous. Let's say I have a joint probability density function of x1 and x2 given as e to the power of minus of x1 plus x2. I am more interested in finding out y equal to x1 by x1 plus x2. So I could very well see that the value of y is decreasing when x2 is increasing. So I can very well write y equal to x1 by x1 plus x2, and now I have to express 1 in terms of other, right? Inverse. So I will try to find x1 plus x2 is equal to x1 by y. x2 is nothing but x1 by y minus x1. So which is nothing but x1 into 1 minus y by y. This is what is becoming my x2. And I can very well see it is differentiable also. So the derivative of x2 with respect to y, if I am looking at the derivative of x2 with respect to y, it is becoming minus x1 by y squared, right? I can do x1 by y minus x1 into minus 1 by y squared becoming minus of x1 by y squared. So first I am able to write g of x1 comma y. I am removing y2 from the plane. So I will write it as g of x1 comma y, wherein I am establishing as e to the power of minus in terms of the inverse function. I am typically looking at minus x1 by y, right? x2 part I am taking out. So I am expressing it as minus x1 by y, and the derivative of it, which I am taking it as minus x1 by y squared. I am taking the modulus of it, making it x1 by y squared e to the power of minus x1 by y. So this is I am only expressing in terms of x2. I am removing x2. I am expressing in terms of x1 and y. So e to the power of minus whatever x1 plus x2. I have established it as, so because it is becoming e to the power of minus of x1 plus x1 by y minus x1. So it is becoming only minus x1 by y. So that's where it finally worked out as x1 by y squared e to the power of minus x1 by y, where x1 is greater than 0 and y is lying between 0 and 1. Now I can very well integrate this one, x1 by y squared e to the power of minus x1 by y. I'll integrate it between 0 to infinity because x1 is greater than 0, e to the power of minus x1 by y dx1. So because now I am integrating it only with respect to x1, I want to integrate it with respect to x1. I can very well take y as constant out. So if I try x1 by y squared, I take out 1 by y squared, x1 e to the power of minus x1 by y. So I'll say x1 by y equal to some t, right? If I say x1 by y equal to t, dx1 is nothing but y dt. So I will write it as 1 by y squared integral 0 to infinity. X1 is nothing but yt e to the power of minus x1 by y is e to the power of minus t, dx1 is y dt. So y squared here is going off. So it is becoming integral 0 to infinity t e power minus t dt. Oh, this is looking like a gamma function because t to the power of alpha minus 1, alpha is 2. I can very well set it as t e to the power of alpha minus 1 into e to the power of minus t by beta. So alpha is 1, beta is 1. So overall this is working out as gamma equal to 2 kind of a value, gamma of 2, which is 1 factorial becoming 1. So the overall density function is becoming 1. So I can very well say that the random variable is having a uniform density function with alpha equal to 0, beta equal to 1. Because 1 by beta minus alpha is the typical this density function associated with a uniform distribution. So I can very well say that the joint probability or density of y equal to x1 by x1 plus x2 will give me a density function value equal to 1. So I can very well say that it is a uniform density function. Then we also have another mechanism of doing the densities associated with the functions of various variables using the moment generating function technique. So this is also used in determining the probability distribution or a density of the random variables when the function is a linear combination of n independent random variables. So especially when I am talking of y equal to x1 plus x2 plus xn, I want to find out the moment generating function associated with all these independent random variables. If I have x1, x2, xn are independent random variables, I want to find y equal to x1 plus x2 plus xn. There is one important rule that says the moment generating function of y of t is product of the moment generating functions of each of these x1s. That's an important rule for us which can help in solving many of the problems. So if you look at this example, find the probability or distribution of sum of n independent random variables x1, x2, xn having Poisson distribution with lambda 1, lambda 2, lambda 3, so on. So we know that for a Poisson distribution, the moment generating function is e to the power of minus lambda e to the power of t minus 1. So if I take each of these distributions, for each one of them, I'll get it as e to the power of lambda I e to the power of t minus 1. Now I want it for y equal to x1 plus x2 plus x3 so on xn. So I will simply take the product of the moment generating functions of all the x2s. So this is becoming e to the power of minus lambda 1, e to the power of t minus 1, e to the power of minus lambda 2, e to the power of t minus 1, so on. So I could very well take e to the power of t minus 1 I'll take e to the power of t minus 1, and this is nothing but lambda 1 plus or minus, if I put outside, lambda 1 plus lambda 2 plus lambda 3, so on lambda n. So I am getting, where is this minus coming? Okay, e to the power of lambda only. There is no minus for my moment generating function. So I am getting lambda equal to lambda 1 plus lambda 2 plus so on. So if we are seeing the distribution of sum of independent random variables having a Poisson distribution, parameters lambda 1, lambda 2, lambda 3, so on, the sum of those such independent random variables x1 plus x2 plus x3 will also have a Poisson distribution with parameters lambda 1 plus lambda 2 plus lambda n. So especially when you are taking for two variables, it would be this, it's a Poisson with lambda 1 plus lambda 2. Three variables, again it's a Poisson with lambda 1 plus lambda 2 plus lambda 3, and so on. Similarly, you take one more example, x1, x2, xn, independent random variables having exponential distribution with the same parameter theta. Now, what is the moment generating function for exponential distribution? Exponential distribution is a gamma distribution where alpha equal to 1 and beta equal to theta. So, based on that, I can very well say that the moment generating function with respect to the exponential distribution is nothing but 1 minus theta t to the power minus 1. So I can do the multiplication of all of them, and because all of them are having the same parameter theta, so multiplication of all of them is nothing but 1 minus theta t to the power minus n. So the moment generating function of y is coming out like a gamma distribution now, right? Because this we are bringing out, if we look at the moment generating function of a gamma distribution, it is nothing but 1 minus beta t to the power minus alpha. So if you try to compare this, here it is becoming beta equal to theta, alpha equal to n. So this is becoming the moment generating function of exponential distribution is becoming a gamma distribution with alpha equal to n, beta equal to theta. So you could very well make a conclusion that the distribution of sum of n independent random variables having an exponential distribution, each one of them having exponential distribution with the same parameter theta, will work out as a gamma distribution with the parameter values alpha equal to n, beta equal to theta. Right? So you could very well use any of these techniques to find the probability distribution and density functions of the different random variables, different combinations of random variables as well. So this is what I wanted to cover as a part of this session. If you have any further queries, you can very well get back to me by giving me a call on the number that I have provided below, or you can even send in an email at vamsidhar@pacegurus.com. Thanks a lot for listening to this session. Thank you very much.